Okay, let's look at this first one. So this was definitely a little bit harder one. And I kind of gave you the hint, what we saw as we were going through, that it looked like what we were adding was increasing by 2 each time. And we've seen this before with squares. So the idea for the first one is we said, well, it clearly doesn't start at 1. Because 1 squared, I mean, that's going to be kind of awkward. But we noticed that we could write 11, and I'm just going to do that. I could write it as 3 squared plus 2. I could then write 18 as 4 squared plus 2. I could write 27 as 5 squared plus 2. So I'm not going to do that for all of them, but that's kind of the idea. Looks like it's the idea here. Now we have a bit of a problem, though, because we don't want to start at 3. We want our sequence to start at 1. So I'm going to make a little change. So instead of it being 3 squared, what I'm going to say is it's 1 plus 2 squared plus 2. So notice I've replaced 3 with 1 plus 2. For the next one, it's going to be 2 plus 2 squared plus 2. So I replaced 4 with the next term in the series. So the next one should be 3 plus 2 squared plus 2. Okay? From there, hopefully what we see is we see that the pattern emerges. So the idea in this case, see if you agree, it's going to be I plus 2 squared plus 2. And again, we should double check to make sure that that actually works. If I plug in 1, 1 plus 2 is 3. 3 squared is 9 plus 2 is 11. If I plug in 2, 2 plus 2 squared is 2 plus 2 is 4. 4 squared is 16. Plus 2 is 18. If I plug in 3, it'll be 27. Okay, so it definitely looks like it's going to work. From there, let's go and finish this up here now that we have our thing. So we know that our series in this case, we're going to start at 1. We don't know where we're going to end yet, but our formula is going to be this. Now remember, in order to find that upper bound, what we're going to do is we're going to take this formula that we found and sub in 102 for a of I. And then we'll just solve this equation. So I'm going to subtract 2 from both sides. And that leaves me with I plus 2 quantity squared. I'm going to take the square root of both sides. Reminder, when you take the square root, you get plus or minus. But, and this is important, sequences, we always go term 1, term 2, term 3, term 4. We don't go term -1, term -2, things like that. So in this case, I can ignore the negative and just solve. In regards to that one, let me kind of shrink that out a little bit. In regards to number 1, again, I recognize it was a hard one. It's hard to find the formula. Question?
What's the difference between you just doing 3 squared plus 2 versus 1 plus 2?
So the problem is, so the question was asked, why not just have it as 3 squared plus 2, 4 squared plus 2, 5 squared plus 2? The problem is, think about what our sequence would look like. Our summation would end up looking like this. You've got to start at 3, and then you're going on forward to the rest of the thing. It's not that it wouldn't work, but we wanted our series to start, we wanted I to be 1 for the very first thing. That's what we want to sub in first. So technically speaking, if you're just allowed to kind of start it wherever you want to, which a lot of times you can, we've seen ones start at different places, that would be fine, and we could do something like this. That would still be fine. But again, we want to start at 1. Other questions that you have? Okay, let's look at the next one. So I wanted to hit this one because there's 2 ways of doing this. So first off, we could do like we did in 7.1, and that is we could just write this out. This starts at 5, it goes to 10, so I could say 3 times 5 plus 3 times 6 plus 3 times 7 plus 3 times 8 plus 3 times 9 plus 3 times 10. Pull out my calculator, get my value. Totally fine, that will totally work. But I want you to notice that this is actually an arithmetic sequence, or I should say series in this case. And if you're not sure, just check it, right? So I'm gonna move this blue stuff down real quick. So let's just check. If we plug in 5, 3 times 5 is 15. If we plug in 6, 3 times 6 is 18. If we plug in 7, it's 21. So clearly this is arithmetic because we are adding 3 each time. So remember, our formula for an arithmetic series for the sum is going to be the number of terms times the first term in the series plus the last term in the series divided by 2. So there's not a lot to see here. There's one little thing that we have to be aware of. So the first term is that value that we found. I know it says it's the 5th term, but it doesn't matter where the series starts. That's the first thing we're starting with. So 15 is our first term. Our last term in this case, I plug in 10. 3 times 10 is 30. I divided by 2. The big difference here is n. N is not going to be 10 because that tells you how many terms are in the sequence. But if you look, right, we did this down here. There's 1, 2, 3, 4, 5, 6 terms in the sequence, not 10. Here's how you find n unless you're just counting them out. You take your upper bound, you subtract it from the lower, add 1. 10 minus 5 is 5, plus 1 is 6. So n is 6. So if you want to find the number of terms, one more time, you take the top number, subtract the bottom number, add 1. That will always give you the number of terms. Okay? In regards to number 2.
Yesterday you said that if you just plug in 1, 2, or 3 times, like the 3i, you said that would be the first term.
So it all depends. So just to clarify the question, it's about where we start,
Well,
right? So you're wondering, why didn't I just kind of like start at 1?
yeah.
So in this case, we have to specifically start at 5. So plugging in 5 is going to be the very first term of our sequence. It's saying, this right here says, when you do your when you do your series, it's going to start at 5 and keep on moving up. So the very first term of your sequence is 3 to the 5th. Okay, it's kind of starting at the middle, but there's still a start, there's still an end. Any other questions? Yeah.
Why is it a 6 again?
The reason it's 6 is it represents the number of terms in the series. So the way we found that is we took the upper, subtracted the lower, and added 1. That will always give you the number of terms in the series. Anything else? Okay, last one. This is based on yesterday's. So hopefully this is pretty familiar with us. So we've got a couple ways of doing this. What we talked about yesterday is what you could do is you could use these 2 as points, find the slope of the line between the 2 points, which is D, and then go from there. I'm going to set it up as 2 different equations. Just that's the way I'm choosing to do this one. But I do want to remind you that's fine. You could find the slope of the line that connects those 2 points, and that is your D. So in this case, though, I'm going to set up two equations. So for the fifth term in my sequence, well, let's see, we got the fifth term equals 14. And we find that by taking the first term times n minus 1, n being 5, minus 1 times d. And then in order to find the 22nd term, our 22nd term is 65. Again, which is created by taking the first term plus the 22nd term minus 1 times d. So now we have two equations and two variables. So we can solve this. So I'm just going to clean things up a little bit here. So we get 14 equals the first term plus 5 minus 1 is 4, so 4d. And 65 equals the first term plus 21 times d. And then I'm going to subtract. I'm going to use the elimination method so that I can get rid of the first term in both of them. So, and I don't want to mess this up. The first terms cancel each other out, and we get this. So in this case, we get d equals 3. Again, all I did was the elimination method. You could have used the slope to find d. That's fine. From there, now that I know what d is, I'm going to choose one of my 2 points. It doesn't matter which. So either this one or this one. I think I'm going to choose the first one. Let's do this. I think I should be able to fit it in here. And I'm going to write a formula for the fifth one. So 14 equals the first term, which we still have no idea what that is, plus n minus 1, which is 5 minus 1. d, now we know what d is. It's 3. So we get 14 equals the first term. 5 minus 1 is 4. 4 times 3 is 12. So it looks like the first term is 2. So our sequence is going to be a to the n equals the first term plus n minus 1 times d, which is 3. In regards to number 3, do you have any questions? Yes.
Could you show finding d the other way?
Sure. So the question was, how do we use the slope? If we wanted to use the slope to find d, let's go and do that. I'm going to just kind of grab these 2 points really quickly. So if we chose to find d using the slope, remember the first point is the point 5, 14. The second point is the point 22, 65. The slope, which I'm going to designate this time as d because it is going to be the common difference, is going to be, reminder, it's y2 minus y1 over x2 minus x1. So in this case, it's going to be 65 minus 14 over 22 minus 5, which is, what is that, 51 over 17, which is 3. From there, note, we're back to this and this are the same. We're now back to what we did in the purple one because that's going to be the same for both methods. Any other questions on that one?
So if you're to combine terms for the an equals 2 plus n minus 1 times 3, would you just do 3 times n and 3 times x1? You
Yep.
just didn't do it all.
Yep. So the question was about simplifying, and again, you simplify as normal. Okay,